Deep within the remote Himalayan gorges, one of the most ambitious engineering feats in human history begins with the raw power of unyielding geology and glacial water. Before a single ton of concrete can be poured, geologists must analyze the structural integrity of the ancient bedrock carved by millions of years of natural erosion. Heavy diamond core drilling rigs push deep into the mountain floor, extracting solid rock samples from hundreds of meters below the surface. Each extracted core undergoes rigorous density and load-bearing testing to ensure the canyon walls can withstand the immense hydrostatic pressure of a mega reservoir. With bedrock parameters verified, massive open-pit quarry operations begin extracting millions of tons of hard granite to supply the project's concrete production line. Inside massive subterranean crushing chambers, giant jaw crushers pulverize boulder-sized granite into manageable stone fragments around the clock. High-frequency vibrating screens classify the aggregate into strictly measured size categories, ensuring an optimal particle distribution for high-density concrete mixing. Miles of automated conveyor networks transport sorted sand and gravel to climate-controlled storage silos to protect raw materials from alpine weather contamination. To guarantee perfect chemical bonding during hydration, high-pressure water cannons wash away every trace of fine silt and microscopic surface dust. Only perfectly cleansed, high-density granite passes moisture and purity inspections before being routed directly into the main batching towers. Standing taller than 10-story buildings, fully automated concrete batching plants run continuous mixing cycles designed to supply thousands of cubic meters daily. Computerized batching systems measure exact proportions of low-heat Portland cement, fly ash, and silica fume down to the precise kilogram. To prevent thermal cracking during mass curing, liquid nitrogen and flake ice cool the concrete mixture down to strict subambient temperatures. Inside heavy twin-shaft horizontal mixers, giant mechanical arms exert thousands of newton-meters of torque to create an ultra-dense, homogeneous slurry. Freshly mixed chilled concrete dumps directly into massive aerial cableway buckets, designed to transport material across the wide canyon gap. High-speed overhead cableway systems span the entire gorge, moving thousands of tons of material daily with surgical position control. At the pore face, heavy pneumatic discharge gates release the chilled mix into massive steel-reinforced monolith blocks constructed in continuous layers. Powerful hydraulic vibrator arrays consolidate the pore, expelling air pockets to maximize structural density and eliminate internal voids. Laser-guided screeds level each layer to sub-millimeter precision, before cooling pipes embedded deep within the block begin thermal regulation. Internal cooling networks circulate chilled water through embedded pipe circuits for weeks, controlling hydration heat to prevent microfracturing. Deep beneath the mountain ridge, excavation teams carve out massive subterranean caverns designed to house the world's largest hydroelectric turbine generators. Engineers utilize sub-millimeter laser surveying systems to align foundation anchor rings, ensuring absolute verticality for heavy rotating components. Simultaneously, heavy steel fabrication plants process ultra-thick high-strength steel plates required for penstock pressure pipes and spillway gates. High-definition CNC plasma cutters slice through thick armor-grade steel, shaping complex bevels for penstock ring segments with extreme heat accuracy. Immense hydraulic rolling mills exert thousands of tons of pressure, curving massive flat steel plates into perfectly round penstock shell cylinders. Automated submerged arc welders execute continuous multi-layer weld passes, fusing cylinder seams to withstand internal water pressures exceeding dozens of atmospheres. Completed penstock sections are moved onto heavy motorized turning rolls, where internal surfaces are prepared for anti-erosion lining applications. At the heavy forge facility, giant stainless steel ingots are heated to extreme temperatures and forged into monolithic main shafts for the turbine units. Giant vertical milling lathes precision machine the forged shafts and runner hubs to tolerances measured in fractions of a millimeter. Despite advanced automation, final hydrofoil blade profiles require master craftsmanship, grinding microcontours to maximize hydraulic efficiency and suppress cavitation. Each stainless steel runner blade is systematically aligned and fitted onto the central crown, forming a fluid dynamic wheel capable of withstanding extreme water forces. Calibrated hydraulic tensioning equipment secures heavy structural bolts to exact mechanical specifications, eliminating any risk of micromovement under operational load. Inside the generator manufacturing hall, master technicians wind hundreds of miles of high-purity copper bars to construct stator coils capable of generating gigawatts of electrical output. The completed stator core undergoes vacuum pressure resin impregnation, sealing every microscopic void within the insulation against moisture and electrical degradation. Before field installation, fully assembled generator rotors are dynamic spin tested on high-speed balancing rigs, measuring vibration down to microscopic displacement levels. Entering the quality control phase, certified inspectors perform non-destructive ultrasonic scans across every meter of welded steel to verify zero internal flaws. Precision 3D laser scanning systems map the physical geometry of turbine runner blades, comparing millions of surface coordinates against digital CAD models. Heavy isolation valves and penstock segments undergo extreme hydrostatic pressure testing, holding loads far beyond normal operational limits to ensure ultimate safety. Specialized anti-cavitation polymer coatings are applied to water passage surfaces, shielding internal metal components from long-term high-velocity water erosion. With every test passed and microtolerance verified, the final quality certification stamp is applied, marking the component ready for heavy transport. To protect sensitive precision surfaces during transport through high-altitude weather zones, giant components are sealed inside multi-layer protective barrier wraps. Custom steel transport frames and heavy chain lashings secure multi-ton assemblies, engineering them to withstand severe vibration during mountain haulage. Massive overhead gantry cranes carefully transfer the mega components onto specialized heavy-haul transport vehicles designed for extreme payloads. Equipped with hundreds of independently steered hydraulic axles, specialized heavy transporters distribute thousands of tons across road surfaces evenly. Navigating hundreds of miles of treacherous mountain highways, heavy transport convoys carefully move components toward the mega dam site. The convoy enters specialized subterranean access tunnels bored directly through the mountain core, descending directly into the turbine hall caverns. Deep inside the powerhouse cavern, heavy dual bridge cranes lower components into deep concrete generator pits with millimeter landing precision. Precision alignment systems guide the mating of the turbine runner shaft to the main generator shaft, completing the core mechanical power train. Substation galleries and high-voltage transformer yards are connected, preparing the infrastructure to route clean megawatt output directly into national power grids. With structural, mechanical, and electrical systems fully integrated, the mega dam stands ready to harness the unyielding kinetic force of the river. As commissioning tests reach final clearance, the colossal hydraulic radial gates lift, releasing controlled water flows through concrete spillway chutes. Immense hydraulic flip buckets dissipate kinetic energy into the plunge pool basin below, showcasing the raw, harnessed power of high-head hydroelectric engineering. Inside the cavernous turbine hall, multi-gigawatt generator units spin in seamless harmony, converting the immense pressure of the river into continuous clean electricity. Ultra-high voltage transmission corridors surge with gigawatts of zero-emission energy, powering distant industrial centers and millions of homes across the nation. Dwarfing all predecessors in scale, structural engineering, and raw power generation, this monumental achievement redefines what humanity can build. Next-gen process. Sourced from nature, forged by engineering, perfected for the future.